So how many people have been to the zoo and you've seen these mold-orama machines, right? You want to get the elephant, you know, you put your 50 cents in or $1 in. You got this injection molding machine, and you put your money in, and then you get this sort of wax animal coming out. You know, I'm talking about injection molding. And what that is you got a mold there. It's got two halves. And they come together, inject the plastic, and let it cool. So the plastic comes in molten, right? Then it cools down. Then you go in to grab your elephant, and it's too hot for a second, right? And you wait, and it cools down. And there you go. That's injection molding. And, what we're talking about here is the cavity that produced the mold, the cavity that the plastic was injected into. And the question is whether traditional manufacturing methods or laser-based manufacturing methods are more compatible with environmentally conscious manufacturing. So we undertook a study, and there were a bunch of us involved. Some of you might know Professor Mazumdar. He developed the direct metal deposition technology we'll talk about here. Okay, so we're looking at two different ways of making a cavity, essentially, for a mold. One way is the traditional way here on the left. You take a solid block of metal, and you just mill it out. Mill out the pocket, back and forth and back and forth. You know, you can't go all the way down usually with the tool, so you're going to have multiple passes along the same length, and you're going to get a certain depth. Now there's an alternate way to do that, and that is to do this in an additive fashion, layer by layer, round and around and around and around to get the same part. The question is, what might have a lower environmental impact? Okay. Direct metal deposition technology, there's some photographs of it on the right. It's laser, in this case a CO2 laser. Basically the laser is focused on a point where metal powder is injected. And you've got basically a sheath gas focusing that powder into a very specific location. You're hitting that location with the laser, melting the powder, and essentially sintering parts layer by layer by layer. So the table moves, or the head can move, and you can build up your part. Full metal parts, layer by layer. Okay? Let's see. One of the characteristics of direct metal deposition is that it has feedback. So in this case, you're looking at sensors, two sensors. You can see them over here also. They're keeping track of the process, looking at dimensional accuracy as well as the accuracy of the material characteristics. And basically making adjustments in process. Adjustments to dimensional characteristics, maybe adjustments to the power of the laser in a closed-loop feedback kind of a fashion. Okay? Does everybody understand what the technology is, what it's trying to do? This is powder metal. Go ahead, Taylor.
What's the scale of these parts?
They can be big. So if you've got like a flatbed, and let's just say you've got like a stamping tool for a car, you can take the head and work on it over that kind of length. You can make small parts, you can make big parts. Other questions? These are small parts. Okay, does everybody get it? Okay, so the level of accuracy you can get is pretty high. You get to 100th of an inch, even a little bit better these days. These are real parts. So you can make real cars with real tools that are made with direct metal deposition. You can have a lot of fun with this technology. So I think everybody knows if you heat a material, generally expands. Well, with this technology, if you mix the powders up, you can actually create some materials that if you heat it up, it contracts. So functionally tailored tools using heterogeneous material characteristics. Pretty cool stuff, fun. Engineers, you got everything, right? It's kind of like a robot. You got sensors, you got materials, you got cars. It's just a lot of fun for the whole family, right? It's just a big toy, but for serious work. So we actually got a grant from the National Science Foundation to explore this idea a little bit. In this case, we're looking at the reversible snap fit. Thursday, we'll talk about end-of-life decision-making, disassembly, basically disassembly, decision-making, look at some characteristics of remanufacturing also. Here, what we proposed was the idea of a disassembly button. So imagine, this was back in 2003, so imagine that you've got, it could be a laptop or it could be a cell phone, and you want to be able to open it easily. Suppose that you had sort of an infrared signature, or just to think about it simply, you could just think about a very special point on the product where if you put a heat source there, maybe a strong heat source, on the inside you'd have these conductive vias that would find their way to snap fits, and essentially, depending on how you design the snap fit, either expand or contract and just allow the product to disassemble itself. Right? It's a pretty cool idea. It actually isn't that hard or that expensive to do. The question is there an audience? But we didn't know if there would or wouldn't be at the time. But we undertook this kind of case study, and again, direct metal deposition, doing similar things with plastics, playing with material characteristics. This is something you can do. Okay. So talking about a comparative life cycle assessment between traditional manufacturing of a mold and laser manufacturing of a mold. Okay. So we're making now, and I actually had the picture on this slide. Imagine instead of an elephant, we're making a block M. Okay, so football team's doing okay, so we want to sell these M's. And we want a mold to make that M, so here's the mold. And our functional unit is a mold. It's kind of boring because it pretty much just sits there in the use phase. Now we're going to compare making that mold using basically milling process and a direct metal deposition process. So let's take a block of metal and we'll just carve out or mill out the M, or sort of layer by layer we'll make up the M. Okay. So our functional unit here, we're just looking at the plates and the machining. We aren't looking at the frame assembly around it, which you also need in an injection molding process. Okay. Here we only looked at energy, which in this case turns out to be a decent proxy. But we're only going to talk about energy here. All right. Questions? What we're doing? Clear?
The cutting laser, it's not the deposition laser?
No, it's a deposition laser. So in this case, we're going to mill. So we're making it, if I go back, we're basically doing this. We're milling it out. So we can mill out the block M, or we can put in all the material around the M, so the M is just left there. Everybody got it? Go ahead.
Framing around like block M is needed.
So you can kind of see it in this picture, right around here. So can you kind of see that outline? So that's the framing. Think of it as framing, but it's just part of the mold tool. It can't be too thin, or else you would, wouldn't be strong enough. Also, you need to inject the plastic. So there's actually a location here to run that plastic in. So this is about as small as you could get. You could probably do a little better. Other questions? Okay, so talking about the scope of the analysis now. Once you make the mold, we assume that they're identical. So whether you do it in laser manufacturing, you do it with direct metal deposition. There are some differences in finishing, and in direct metal deposition, you've got some need for a greater finish, more finishing process. So we're going to ignore that here. You've got the basic steel coming in. That gets melted, refined. So think about the steel works in Indiana, and we're going to make some casts there, ingots, big chunks of metal. They're going to get cut into slabs. They might be rounds, they might be plates. And if you're making, if you're going the conventional route where you're just going to mill out the M, you're just going to take that plate or that block, and that's your input to the milling process. Okay, so you're just basically going straight down the middle here, but you also have some, and it's not all scrap. You have some fraction of new steel coming in. Okay, so that's a traditional way. Now, it would be really efficient if at the steelworks you injected some nitrogen gas and formed the powder right there. But that's not what happens. What happens is, so we call that the direct powder creation process. What usually happens is you just take those plates or slabs, you remelt those, and then make your powder. So it's inefficient. So we call that the indirect powder creation route. And clearly that's going to require more energy. So if you look at this plot, you're looking at, this is the conventional, just making the plate here that's being milled out. This is specific energy. This is megajoules per kilogram. So this is just the material production. So we're not talking about the milling. We're not talking about the DMD. We're just talking about the creation of plate, the creation of powder. Okay? If that powder is made indirectly, you see that it's a little bit higher than just using the plate itself, because essentially you're remelting that plate to make the powder, and that atomization process requires some energy. But if you were to go directly, we estimate that in terms of the material production, it would be a significant reduction in energy. Is this making sense to people? Questions? So let's move on then. We've got the material. The block, if we just look at we can call it a block or we can call it a plate. That block is going to be 11 megajoules to make. That's just the material component. Now we're going to mill out the M. So that's CNC. Now, the surface finish on this really matters because the outside of the M is what the customer is going to see. But the inside doesn't really matter, right? So those of you who know machining, you're going to rough cut a big chunk of this to blast out the interiors. And you can do that as fast as you can. But then when you get to the edge, you have to be really careful about the surface finish. So there's the roughing cut, and then there's a finishing cut. And you see here that, and we actually don't break that out. No, we do. So the total here in terms of milling is about 7 megajoules. Okay, and what you see here, this is the specific energy consumption, SEC. Roughing, you can basically operate at 24 megajoules per kilogram of material removed. For finishing, it goes up by more than a factor of 10, more like 13 or something like that. So that finishing, because you're going to take a small tool and you're going to move slowly and you're going to, cut just a little bit of material at a time, that specific energy consumption goes up a lot. 75% of the process energy is finishing, even though it's a small fraction of the material actually removed. It's just the stuff on the edge. Does this make sense to everybody? So what do you learn from that? Geometry matters. This is just the conventional process now. We looked at the material, 11 megajoules. Now the milling is going to be an additional 7 megajoules. And you're going to get up to about 18 megajoules. Okay, everybody following? Okay, so let's take a vote. Does direct metal deposition require less energy or more? Who says less? All right. All right, so maybe 10% lower, less than 10%. All right, how many think that the milling is going to be lower? All right, a few more. All right, so DMD has more energy. That's our class vote. The result is yes and how, as the kids would say, right? So the raw material here is about 11 megajoules, so roughly the same ballpark. But when we look at the DMD process, we're talking about 3 gigajoules. So it's a lot more energy. Now I need to put a little bit of a caveat on that because we had an old laser. So our estimate is actually, you could probably get this down by a factor of 10, but not more than a factor of 10. So either way, you're about 10 to 100 to 1,000 times more energy in the direct metal deposition process. You see the need for a better finish. Again, this was about 10 years ago. Technology's come a long way. Finish actually you can get these days are pretty good, but you still need to do some cleaning up generally at the end. Okay, so we can look at some of the same types of plots that Professor Herman was looking at, right? Looking at aluminum die casting, right? And this is, to clean up, you got to get dirty. So, we looked at the energy signatures. We saw a lot of potential for energy improvement, right? I mean, just turning the laser on, but not using it, you're at 49 kilowatts, right? So think about a 100-watt light bulb. You turn this thing, just turn the machine on, you're at 49 kilowatts. It's not necessarily the fastest process, so it's running for a long time. Next thing you know, you've got numbers looking like this. So your task-based specific energy consumption is somewhere around 7,800. So that's a lot more than finish milling. Go ahead.
Processes, is the finishing part the same for both?
Assume there's no
Similar?
finishing in DMD. We're not looking at that.
Okay.
I don't have any numbers for that here. So, we like to, in LCA, say the functional units are the same. In this case, they're not exactly the same. I mean, you can tell that the parts look a little different, right? If I compare this one and I compare this one. Andrew?
Part that's pretty straightforward. If you got into something that required many more sort of axes, like if you did a 5-axis mill where you're basically using fine heads the whole time, the difference in energy utilization is going to be significantly different. When for a mill, this is a piece of cake to cut that out. I mean, it's nothing. But if you started doing turbine blades or milling out a engine block or something, have you looked at, as you increase complexity, how that affects the ratio?
How about this part?
All right.
Yeah, it's all about part geometry. Andrew's exactly right. I think I got a video to explain what he's talking about. I know not everybody's a master machinist in the same way, so let me see if I can get that up here really quick. So you see the mirror. All right, here we go. So try milling that out again and again and again and again. It might make more sense to go layer by layer on that. So look at it this way. So you get the idea. Here, you've got a very different deposition to removal ratio, right? So you can think of it as your solid to cavity ratio. Here you've got a lot of cavity, and in the last case here, you really didn't with the M, okay? Okay, it's trying to move past here now. Oh yeah, there it is. All right, good. So now if you look at that was the back of a mirror used in a space application. Okay, if you look at that part, let's forget the additional efficiencies you can get with the direct metal deposition. It still wins. So we're looking at the process volume here, the process time, even the process energy for a laser that was relatively inefficient. Right? So you can win. And it goes directly to the point that it's really about the geometry in this kind of a process. Right? So even a suboptimal laser deposition process can do well. Now, if you look at the commercial versions of this technology, you can do it with a lot less energy and with much better surface finish. In fact, the surface finish here wasn't that bad. You can actually see it. Okay? Does everybody get the point? Geometry matters. So, you can't, these blanket statements about technologies, they're hard to make, particularly in manufacturing now. There's other ways that you can put an energy-intensive technology like DMD to work. In this case, we're looking at what are called conformal cooling channels for injection molding. So let's go back to that cell phone. And let's suppose that, I need a certain number of injection molding machines to make the housings for the cell phone. Now, I would like those cell phone casings to cool as quickly as possible. So the way to get the cooling to happen faster is you put cooling channels in. Now, the way that's done is you just drill holes through there. All right, so you just drill some holes, then you run water through. So cooling channels are a common practice in manufacturing. What you can do with this technology is actually conform those cooling channels. So, drilling's a straight process, right? You can't, drill and twist and turn. But if you're building the mold up layer by layer, you absolutely can. So this is looking at examples of cooling channels. And what happens is, here's, this looks a lot, again, like what you saw Professor Herman showing with die casting. Here we look at the energy consumption just for, one cell phone. In this case, a hydraulic machine or an electric machine. The hydraulic machine uses more electric power. This is over time. Maybe it's a 35-second operation. If I've got conformal cooling channels, maybe I can get that down to 20 seconds. And if I integrate under the curve, I win. And I can produce more parts with fewer machines. So I win. All right, so conformal cooling channels not only can increase productivity, but they can reduce environmental impact by reducing energy consumed. There are other ways you can employ a technology like this. So imagine using it to apply coatings. So we've got forgings for crankshafts. And what if I take the forging tools and I put highly resistant alloy coatings on the top so that the tool life increases by a factor of 3? Right? You can increase manufacturing system productivity because you don't change out the tools as often. And of course, there's a lot of environmental savings. We calculated millions of pounds of air and water emissions per year. Now, if you do this kind of thing, because you're just taking a conventional tool now and you're just doing a very modest deposition on the top of it, very strong material. This is looking at a seat belt clip. Another way you can put a technology like this to potential environmental use. Now, here we're looking at die casting, and we see that there's a big copper block. So basically, you've got tool steel that has been directly deposited on top of copper. Why do you think they use copper? Go ahead.
Block.
Yeah, chill block. So you can conduct the heat out of the process. It cools faster. You can make parts faster. About 25% faster. Right. In so doing, then, you can actually reduce your CO2 emissions in process. Because not only you can make the parts faster, you're going to use less energy in the process. Ultimately, you win. And we're talking major electricity reductions by doing it. Now, there's an environmental downside to this. What do you think it is? Using DMD to put tool steel on copper. Hard to separate? Matt, is that what you're going to say? Jared, anything else?
The shape of the cavity is going to wear pretty quickly because it's copper.
That turns out to be less of an issue here. It turns out to be much more about the mixing. So if you've got steel, yeah, gotcha. So if you're depositing steel directly on copper, you're going to have a hard time recycling the copper, and you have a hard time recycling the steel. I mean, even if you go in here and mill it out, you mill the top, I mean, you kind of see, like, you've got mixed materials here. And essentially, steel, or let's say copper, is a knockout element for steel and vice versa. So recycling, good luck with this. Now, you may decide that the energy benefit outweighs the material benefit. Right? In this case, we assume that the product was discarded, and you still win in terms of energy. But again, thinking about materials and availability of materials for future generations may or may not be a good thing. Right? People understand these kinds of applications? Things you can do. Here's another example. This is getting us into remanufacturing now. So let's take that block M. And football team's just doing so-so this year. So let's suppose instead of the block M, we just want to change it to a small m for mom or whatever. Right? So you're not going to sell the block M, so you're going to sell this M instead. Now, what would you do before is you just take your old tool and go recycle it. what you can do with a technology like DMD is you can couple it with milling, for instance, in this case. You can mill out some parts, you can DMD some parts, and with very minimal manufacturing time, effort, cost, change tooling over. Right. Now, this seems like a play example, but they actually did this for real tooling on a real car. This was a side panel for an automobile. It was going through a stamping tool changeover from, I think it was 2002 to 2003. So rather than making a whole new 10-ton tool, what they did was they milled out basically the features of the old one and then used DMD on top of it to make the new tool. Right? So you go from old tool, here's the material removal, material addition. Now you've got a new side panel tool for a vehicle. Okay, so clearly, not just in environmental savings, which we calculated at about a ton of carbon dioxide, but the bigger cost is the bigger issue is the cost savings and the lead time reduction. Right? Kinds of things you can achieve with this. John Michael?
Would you always have to be adding material to do this?
No, you wouldn't always have to add material. You're hard pressed to come up with examples where you would only remove material, but you can come up with some. If you went from one block M to a bigger block M, and you had enough framing material, you could do that. Just removing material. Kawi? Yeah, so this is where you get into some of the same issues we talked about metal stores, right? The capital cost, right? The payback time, the culture, right? So you need some different type of labor to interface with this kind of system than you do with a traditional system, and you've got labor contracts, and there is a company called Precision Optical Manufacturing, POM, that Professor Mazumdar runs, and they're selling these machine tools. He doesn't quite have his own personal jet yet, but maybe he will. We'll see. But you do run into these same kinds of capital cost, variable cost trade-offs that we've talked about many times this term. Other questions? Yeah.
Did you have any quality issues with the added material to the mold?
In this case, no. In the case that we did in our own lab, yes. You saw that M didn't look like the highest quality part. In terms of the production machines, you have a much higher quality finish. This was a usable tool. Other questions? Okay, I mean, clearly you got to think about not just the energy waste, but there are other issues, right? So you're blasting metal all over the place, right? So you need to filter the air around this process. It turns out to be trivial, but you need to do it. You need to think about it. You've got carrier gases here. You got to think about mixing materials. That's going to happen here. And then, maybe this rebound effect that we talked about before, because you can imagine, making one of these on your tabletop, right? Now imagine, everybody had one of these at home. And so the new uses for making metal parts maybe that you couldn't have before, because this is sort of one-stop shopping, right? So you can think about, added production from the increased efficiency. Or because this is a fairly clean process, just enclose the machine, put a HEPA filter in there, you could make a tabletop version. And they're talking about this for military applications where you got to repair parts out in the field. Okay. So this is sort of it's kind of a busy slide, but it's sort of a vision for how you can do something like this, right? Where you're looking at, kind of the process, and imagine you could take in, an old part and do some inspection on it. And then you can put some CAD in, computer-aided design files for your new part. So basically you can imagine a computer system that actually does an in-process inspection, comes up with a whole milling / DMD process plan, and makes new parts out of it. So you can it's not science fiction. You can do this. Actually, all the elements have been proven. All right? But the question really is, okay, well, what's the incentive? We go back to the same kinds of questions that you're already asking. Okay, well, you know, does it really cost me all that much to throw out my old tool? What is the capital cost? What is the payback? What about the ability to train operators? Would the operators be accepting of the technology? You know, how many of my peers have adopted this technology? Right? So those same questions come up in die casting, laser manufacturing, metalworking fluids. This is sort of becoming a recurring theme. Right? Now, and basically what we're concluding here as we wrap up, just that, you know, you can use a highly energy-intensive technology to reduce energy consumption on a life cycle basis. It's counterintuitive, but you can do it. You run into all the same barriers, but you know, we think that, you know, this remanufacturing aspect, which we'll talk a little bit on Thursday if we have time, might spill it a little bit into Tuesday if we need to. But talking about remanufacturing is a nice niche application where you can, you know, not say, well, it's either milling or DMD, but we're going to do some fraction of both. From the environmental and cost and lead time and turnaround perspective, you have some opportunities there.